Let's talk about Coulomb's law. What is Coulomb's law? Till now we have seen there are two types of charges and the properties of those charges, right? Now we will talk about what is the force formula for the two charges or many charges placed apart from each other, right? Okay, so that is given by Coulomb's law. We know, suppose if I have two charges Q1 and Q2, and let's say the distance between these two charges is r, or rather the distance between the center of two charges is r, and these are q1 q2. Then the Coulomb's law states that the force between the two charges is given by this formula, F is equal to k q1 q2 by r square, right, where F is the force and this k is a constant, q1 q2 are the charges, and r is the distance between the centers of these two charges. Okay, now if these two charges are like charges, that means positive positive, or negative charges, again negative negative, then it will be repulsive force. If they are of opposite nature like positive and negative or positive and negative, then it will be attractive. But the formula remains the same, which is k q1 q2 by r square. So since this is an electrostatic force, I will write over here as E. Okay, now k is a constant. What is that constant? What is the value of that constant? I will tell you now. The value of this constant k is 9 into 10 to the power 9. Now what is this unit, right? What will be the unit of this? The unit of this is, see, if I write k like this, Fe into r square upon q1 q2, then you will be able to write the unit. This is Newton meter square per Coulomb square, right? Newton meter square per Coulomb square. This is the value of k itself. Okay, now what is the value of k in terms of this another constant? This is 1 upon 4 pi epsilon naught, right? What is epsilon naught? Epsilon naught is defined as permittivity of free space. Permittivity of free space, or you can say permittivity of vacuum. Permittivity of free space, or you can say permittivity of vacuum. And now value of this epsilon is going to be 8.85 into 10 to the power minus 12. Now what are the units? See, k had a unit Newton meter square per Coulomb square. 4 pi will not have any unit, so epsilon 0 units will be inverse of this. So you can write this as Coulomb square upon Newton meter square. This is going to be the value of epsilon 0, right? Okay, now what we are going to do is we are going to do some questions. Okay, so now this is positive. If this is positive, it will be repulsive. If both of them are negative, it is repulsive. If both of them are opposite nature, then they will be attractive, right? That is the thing. Okay, let's do question. One question we can do here. The question, if you see the nature of the electrostatics force, that is k q1 q2 by r square, this is a inverse square law, right? Similar law we have studied already in the 11th standard, that is G m1 m2 by r square, right? So there is a similarity between the Coulomb's law and the Newton's law of gravitation, right? There is a constant G, instead of that k is there, q1 q2 instead of that m1 m2, and r is the distance between these two particles, right? Okay, so now see the difference between this gravitational force, this I will write G over here, and the Coulomb force is that the gravitational force is always attractive, but the Coulomb force can be attractive and can be repulsive as well. One more difference is that gravitational force does not depend upon medium. If you have two masses, the gravitational force of attraction between them will not depend if you put them in water, if these two bodies in water, put them in vacuum, or put them in any other medium. But the Coulomb's law, Coulomb's force will depend on the medium, on the presence of medium, right? That is one thing. And gravitational force is a weaker force compared to the Coulomb force. We will see why it is weaker. Let's do one question. Okay, find the ratio of Fe by Fg. Okay, find the ratio. Okay, this is the ratio itself. Why I'm saying ratio Fe by Fg. for two electrons placed 1 meter apart. Okay, we have two electrons, and as I said, electron will carry a mass as well. So two electrons I have kept 1 meter apart. You have to find out the ratio between the electrostatic force and the gravitational force between them. So let's look at that question. See, you have these two electrons. Each will have 1.6 into 10 raised to minus 19 Coulomb charge with a minus sign. This is also minus 1.6 into 10 to the power minus 19 Coulomb. And the distance between the two charges in 1 meter. Okay, now the mass, exactly, the mass is 9.1 into 10 raised to minus 31 kg and 9.1 into 10 raised to minus 31 kg. These are the masses. The value of K is already known, is 9 into 10 raised to 9. What is the unit? Newton meter square per Coulomb square. And the value of G is 6.67 into 10 raised to minus 11 Newton meter square per kg square. If I put these values in this, then I will be able to get the answer. So let's do that. Fe upon Fg is equal to, Fe is K Q1 Q2 by R square divided by Fg, which is G M1 M2 by R square. Now R is same in both the cases, so I can eliminate it, and then it will be K by capital G Q1 Q2 by M1 M2. What is K value? 9 into 10 raised to 9 into Q1 into Q2 is minus 1.6 into 10 to the power minus 19 into minus 1.6 into 10 to the power minus 19. So this will be 1.6 into 10 to the power minus 19 square divided by 6.67 into 10 raised to minus 11 into masses. Two masses are there. That is 9.1 into 10 raised to minus 31 square. Okay, I will check if it is visible or not. Just visible. Okay, so let me do a calculation here. Okay, so let me write here 9 into 10 raised to 9 into 1.6 square into 10 to the power minus 38 divided by 6.67 into, that will be 10 to the power minus 62, and this is minus 11. Okay, minus 62 minus 11 will be minus 73, right? Yeah. Okay, so one of this 9.1 and this is approximately 9, so I can cancel out this one of this. This is 2.56 divided by 9, approximately 9, and I can take this, okay, 6.67, let it be, into 10 to the power 9 minus 38 plus 73, right? Okay, if I take it approximately 10, what we can do is this. Okay, let's do this first. This is minus 29 plus 73. This will be 34, right? 10 to the power 34. No, 44. It will be 44. 10 to the power 44. This will be 10 to the power 44, and this is 2.56 upon 9 into 6.67. Okay, if I take a 10, if I multiply by 100 on this, so it will be 256 upon 9 into 6.67. I will get some integer here, not integer, some value. Into that will be 10 to the power 42. See, what I am interested is only in the order of magnitude. Okay, the order of magnitude 10 to the power 42. So if I take the ratio of electrostatic force and the gravitational force, you can see the difference. This is 10 to the power 42 times larger the electrostatic force is 10 to the power 42 times larger than the gravitational force between the electrons. You can see how much strong that is. It's not even a billion, okay, not even billion times billion. It is not even billion times billion also. It is 10 to the power 42, staggering 10 to the power 42, right? So that's why it is a stronger force, electrostatic force. Okay, now more stronger than this force, there is one more force which is called strong nuclear force, right? According to Coulomb's law, positive charges will repel, right? Positive charges will repel. But have you ever asked a question that if it is true, then how come in a tiny nucleus all the positive charges are packed together? Because they should repel, and that nucleus is very tiny. If you compare the size of the cricket stadium as the size of the atom, the cricket ball is the size of the nucleus. So that much small space and all these positive charges are stuffed together. How is it possible? Have you ever tried asking that question? If you don't know this, the answer to that is there are no Coulomb force in this. When they come sufficiently close, lesser than 10 to the power minus 15 meter, in this range, Coulomb's law is not at all valid. Coulomb's force will not be there, okay? It will not be valid, the Coulomb's law. You cannot write the equation like this. There will be a nuclear force, a strong nuclear force, okay? So that's why in nucleus, these two will be attracted to each other, okay? So that in more than this distances, Coulomb's law will take over and they will move away, okay? Right, we will see the limitations of Coulomb's law in after these things, okay? Yeah, let's do another question. We have two charges, okay? Let's say this is Q, this is Q1, Q2. The distance between them is R, okay? Now it is given that the forces between these two charges is F. The question is, what would be new force? What would be new force if the distance between them is made half? Distance between them is made half, and one of the charges is doubled. One of the charges is doubled, right? Let's do this question. Then options I will give you. Options I will give you: 2f, f by 2, 8f, and f by 8. Let's do this question. Okay, so the thing is, initially, I think you should try this question. Then you can, and then I will do. Okay, so the two charges are there, Q1, Q2. Then the force between them initially is K Q1, Q2 by R square. Now the new force is, let's say, F dash. Okay, now one of the charge is doubled. Let's say this charge is doubled. So this will become 2 times Q1. Instead of Q1, I will write 2 times Q1 divided by this distance is made half. So it is R by 2. So this is R square by 4. So this is going to be 8 K Q1, Q2 by R square. So this is going to be 8 times F, right? So the answer to that is 8F. Okay, so this was simpler question. Let's look at the next question. Okay, so there are two charges. Let's say this is Q and this is Q, identical charges. The distance between them is D. Initially, the force between these two charges is F. Now, the question is, what will be new force? What will be new force if 50% of left charge, left means this one, is added to the right one? Okay, what will be the new force? That is, yeah, that's what they are asking. The option for this I will tell you. Yeah, so option to that is 1 F by 2, F by 4, 3 F by 4, 3 F by 2. Sorry, 1 is F 1 is F. Okay, let's do this question. You can try this question yourself. Now many people, what they will say is, okay, 50% of the charge is transferred from here to here. Eventually the total charge is same, right? So that means the force has to be same. They will say it is the correct option. But the answer to that is not this. It is not correct answer. Why? I will tell you. See, if 50% of this Q charge is transferred here, 50% of Q is what? Q by 2, right? So now it will become Q by 2 only. And this is another charge Q, and Q plus Q by 2. Q plus Q by 2 is how much? 3Q by 2. Now this is the distance d. Initial force was F equal to KQ square by d square. Now the new force, let's call it as F dash, is going to be K Q by 2 into 3Q by 2, which is 3Q square by 4 into d square. So this is 3 by 4 F, right? 3 by 4 F. So this is F. So 3 by 4 F will be the correct option, this one. Okay, the force will be reduced. It doesn't depend upon the total charge. It depends upon the multiplication of the two charges. Let's look at another question. Okay, there is one charge. Let's call it as Q. And there is another neutral body, correct? The distance between their centers is D. The distance between their centers is D. I will take it as R. I'll take it as R. Okay. Now the question is, I want to transfer some charge to this body, let's say Q, right? Out of this Q, capital Q, I want to transfer this some charge Q to the body. Then of course, if it is positive, let's assume it is positive, then positive charge will only be transferred, right? Then there will be a repulsion between these two charges. I want to find out what charge small q should be transferred here so that the repulsion is maximum. Okay, so let's try that question. If I have to transfer this small q charge from here to here, then eventually what will happen? This will become q minus q and this charge will become q. The distance between them is r only, right? Okay, now the new force will be K times Q minus Q into small q divided by R square. Now I want to maximize this force. If I want to maximize the force and I want to find out the small q charge, then I will take a derivative of that with respect to q. I want to maximize this force, right? So if I do dF by dq, then what I will get? Okay, so if I multiply this K by R square, Q into small q minus q square, right? Okay, I have to take a derivative of this with respect to small q. Now K and R are constant, so let them go out. So this is K by R square. And if I take a derivative of this with respect to small q, it is q minus 2q. Now if I set it to 0, because to maximize it, I have to set it to 0, then you will get q is equal to 2q. So q by 2 is equal to small q. Q by 2 is small q. So that is what is q. So you have to transfer half of q. If you want to transfer the charge to maximize the repulsion, you have to transfer half of that charge. Then only then you will get the maximum repulsion. By the way, you can take a double derivative and check if it is negative or not. If it is negative, then it is maximum. Yes, it is negative. It will be negative. Okay.